Our presentation today will focus on the Vortex bladeless turbine and how it turns wind energy into an oscillatory system that produces electricity.
The phenomenon that allows this system to operate is known as vortex-induced vibrations. This occurs when wind passes around a structure and a fluid's property known as Kármán vortex street is created behind the structure, as can be seen in the top picture. As the velocity of the fluid increases normal to the surface of the structure, the property causes vortices to form on both sides, which create a lift force on the structure that is perpendicular to fluid flow. The perpendicular force causes lateral movement in the structure to begin. When the fluid reaches a certain velocity in relation to the structure's own natural frequency, the shedding vortices begin to oscillate, as can be seen in the bottom picture. If the natural frequency of the structure and the frequency of the shedding vortices become aligned, the vibrations property of resonance occurs. This resonance causes the vortices to be shed at the same frequency of the oscillations, creating the vortex-induced vibrations.
The resonance frequency of the structure has a small range known as the lock-in zone. While operating at frequencies inside this zone, the structure can force the vortices to be shed at the same period of its own natural frequency, even if the velocity of the fluid force on the structure is not within the range to create the correct frequencies of shedding anymore. Frequencies inside the lock-in zone create the largest oscillation amplitudes due to this force synchronizing. Many current studies of the lock-in zone are focused on the relationship between the Struhel number, which is a measurement of the vortex shedding frequency of cylindrical structures, and the Reynolds number, which is a measurement of turbulent fluid flow. As can be seen in the graph, there is a zone of maximum amplitude where these two properties harmonize.
Many studies have been done on the design of the mast. The cylindrical cross-section has been clearly proven to be optimal, but the taper ratio of the diameter of the mast is still being studied. As seen in the left set of pictures, a negative or positive taper ratio has significant effect on the synchronizing of the vortex shedding along the height of the mast. The vertical mast of the turbine, pictured in the middle, is simplified down to be modeled with a very familiar mass spring damper system, pictured on the right. This basic system only has one natural frequency at which resonance can occur. This limits the ability of the system to be able to harvest energy at only a small range of fluid velocities. To increase the capability of the turbine, a tuning system was designed to extend the range of the natural frequency and create a larger lock-in zone of resonance for the structure, thus creating a much greater operating capacity for the turbine.
The magnetic tuning system, modeled as B in the top picture, is composed of a ring of magnets on the inner wall of the mast and a stationary magnet inside the center shaft of the mast that have the same polarity. As the mast bends in any direction, the central magnet tries to force the mast back into its vertical position. Its design allows it to function in two capacities. First, it acts as a compression spring with a nonlinear elasticity. As the amplitude of the oscillation of the mass increases, so does the frequency of the oscillations due to the increasing restoring force of the same poled magnets. This allows the turbine to operate at much lower fluid velocities than the standard damped harmonic oscillator model because of the nonlinear spring force that exponentially increases the amplitude of the lower oscillation frequencies until they can reach the lock-in zone resonance of the structure. The second job is the creation of electricity through a magnetic alternator. As the mast bends, the ring of magnets inside the mast being forced towards the similar poled magnet in the center of the mast causes a magnetic field to be created around a coil that generates power. One recent study was conducted to investigate the implementation of both similarly and oppositely poled magnets to be used in combination to even further enhance the lock-in zones and power generation by increasing the spring force as seen in the bottom picture.
A big advantage of this system is that at high fluid velocities, the system has a naturally built-in safeguard against damaging moving parts. The bladeless turbine system just simply stops vibrating at high velocities due to a decoupling of the frequency of the shedding vortices and the natural frequency of the structure. As the period of these frequencies move away from each other, the oscillation of the structure lessens, which decreases the shedding of the vortices. This stops the resonance from occurring, and the perpendicular lift forces that created the lateral displacement of the mast are overpowered by the drag forces of the high velocity fluid, which stops the system from oscillating. Studies done on this topic show at high fluid velocities the frequencies stop exiting each other and cause the oscillation amplitudes to greatly decrease, as can be seen in the picture on the right.
In conclusion, we believe this new idea of harvesting energy through vibrations is a great path forward in renewable energy, and the concept has endless possibilities of applications that we look forward to seeing implemented in the future. Thank you for viewing, and please let us know if you have any questions.